related queries, call us at +1 678 648 4277. You can mail us at support@solidworksamenthelp.com or reach us at https://www.solidworksassignmenthelp.com. Problem 1. You did such an outstanding job in the engineering department at Unique Unicycles that they gave you a promotion to the R&D department. Your first assignment there is to study a new material developed by your competitors on Unique Unicycles. The material is a composite composed of unidirectional fibers in a polymer matrix, Figure 1. While another research scientist determines what the fibers in matrix are, your boss Dr. Van Vliet asks you to determine the stiffness tensor components for such a structure in terms of Young's modulus and Poisson's ratio. Figure 1. A composite material comprised of unidirectional fibers in a matrix. Solution. From Figure 1 we see that there is some symmetry to this structure. In particular, it is composed of 3 orthogonal axes with fourfold rotational symmetry along the x-axis and SolidWorksAssignmentHelp.com. Twofold rotational symmetry along the y and z axes. Therefore, this structure is tetragonal and has 6 independent elastic constants. Consider the strain if the composite is loaded by a force F along the x-axis, which I will refer to as the one direction. If the fiber and the matrix are well bonded, they experience the same strain such that. Where is the strain in the composite, matrix and fiber, respectively? However, the resulting stress in the fibers is different because of the different Young's moduli in the fibers and matrix. Note that because we know nothing of the fiber or matrix microstructures, we are treating them as isotropic. The stress in the fiber sigma F11 and matrix sigma M11 are therefore, where EM and EF are the Young's moduli of the matrix and fiber, respectively. The total applied force must be in equilibrium with the total force due to the stresses in the fiber and matrix. The internal force is given by multiplying the stress by the area of the fiber or matrix it acts on. If the total cross-sectional area of the composite is A, then SolidWorksAssignmentHelp.com. The cross-sectional area of the fibers and matrix are given by the total area multiplied by the volume fraction of fiber or matrix. Thus the force acting on the fibers and matrix is given by substituting our definitions of strain and dividing by A gives from this equation. We can see that the modulus of the composite along the x-axis E1 is now consider if the composite is loaded along the y-axis, which I will refer to as the 2 direction. The fibers and matrix will experience different strains. The total strain 2 will be the sum of the strain in each component, multiplied by the volume fraction, such that the stress applied sigma will be distributed equally over both the fibers and matrix, and therefore we can write SolidWorksAssignmentHelp.com. From this equation, we see that the modulus along the y-axis E2 is. Furthermore, because the unit cell of the composite is the same along the y and z direction, e.g. the composite has a tetragonal structure, E22 equals E33. We can also do a similar analysis to determine the shear moduli G12 and find where GM and GF are the shear moduli of the matrix and fibers, respectively. Again, because of symmetry, we know that G12 equals G13. For the shear modulus G23, we know that the YZ plane, or 23 plane, is an isotropic plane. Therefore, where nu23 is Poisson's ratio that relates the strain in the 2 and 3 direction. SolidWorksAssignmentHelp.com. There will also be other Poisson effects in the composite. For example, the 22 and 33 will be equal to minus nu1211 for an applied strain. Note that because of symmetry nu12 equals nu13. With all of this information, we can begin to construct a compliance tensor for the composite. Note the factors of 2 in S44, S55, and S66. These are a consequence of converting from mathematical strain to engineering strain. With the exception of our Poisson ratios, the other terms in this tensor are in terms of the component properties and volumes. Let us now do this for the Poisson ratios. Consider a sample section of the composite, figure 2, with a stress applied along the x-axis. The sum of the change in length of the fibers, delta F, and matrix, delta M, in the y direction will Solidworks assignmenthelp.com equal the change in length of the composite, delta C, along this direction. We can write these changes as, we know that along the x-axis, and therefore, or. Once again, because of symmetry nu12 equals nu13, as we have implied already in writing the compliance tensor as we did. The Poisson ratio for the isotropic plane nu23 is a little more complicated, but if similar principles are used, we find Solidworks assignmenthelp.com. With all a composite's elastic constants now defined in terms of the volume fraction, Young's moduli, shear moduli, and Poisson's ratios of the matrix and fiber, we can compute the stiffness tensor sig by taking the inversion of the compliance tensor sig. This can be done by hand, but would be more easily done using some mathematical software such as Mathematica or Maple. As you have found, the inversion is a large messy matrix which I will not present. Figure 2, a sample section of the composite. Solidworks assignmenthelp.com. Problem 2. Two isotropic materials, A and B, are being considered for use in shoe insoles. When used as insoles, the average strain with respect to time, T, of the materials is that presented in the spreadsheet posted. A. Derive a model that accurately describes each material's response to the applied stress. Plot the result of your model along with the given data. Solution. Material A has an immediate response to the stress and strain is constant with time. We recognize this behavior as characteristic of a linear elastic solid. An appropriate model for its stress/strain behavior is therefore Hooke's law, K equals sigma/E. For material B, we see that there is an instantaneous response with the applied stress followed by a strain that is dependent on time. This appears to be a linear viscoelastic material. The constitutive models we have for these materials include the Maxwell solid, Kelvin/Voigt solid, and standard linear solid. We can eliminate the Maxwell solid because it cannot very accurately predict this type of strain response with time, as discussed in lecture. Solidworks assignmenthelp.com. The solution to the Kelvin/Voigt model is where sigma is the initial stress, E is the Young's modulus, T is the time, and tau is the relaxation time. If we plot this with our data for material B, figure 3, we see that we can accurately predict the strain at later times, but not at earlier times, especially the instantaneous strain we observe at t equals 0 s. We therefore must consider another model. Because the Maxwell solid can accurately model instantaneous strains, how about a standard linear solid that is a combination of the Maxwell and Kelvin/Voigt solids? From the Maxwell solid and Kelvin/Voigt solid we have, respectively. Taking the best parts of these two equations, we write an equation of the form and Solidworks assignmenthelp.com. Where tau and tau sigma are the relaxation times for fixed strain and stress, respectively, and ER is the relaxed modulus. To understand ER, look at the physical model of this system in Fig. 4, in this system, as time goes to infinity, where E1 and E2 are the respective moduli of the two springs. Or, now imagine that a stress sigma is applied and held constant, as is the case in our problem.